Hi, today we're going to wrap up our discussion of scatter plots, that is, graphs that show the relationship between two numeric values. And we want to today address something that should have been nibbling at the back of all of our minds. You know, we've been talking a lot about linear correlation, but the truth of the matter is there are lots of scatter plots that do not produce linear results. Okay? So today we want to just take a brief look at how you can use some transformations to change actually the shape of data so that you can use our linear diagnostics on it. That is, we want to see how we can change curvy data so that it looks more linear, so that we can come up with a linear regression line and a value of Pearson's correlation coefficient that will fit that data. We're going to begin by talking about exponential growth and decay, which we're familiar with in high school. We've looked at this a lot. The data that you're seeing here is a result of an experiment where we counted the number of coin tosses it took before we got ahead. And you will see that 89 times out of the total number of trials, a head came up on the very first toss, which, you know, there's a 50-50 chance that it would. If it had to go to 2 tries, 60 times we got the head on the second trial, and that's how it goes. If we get all the way down here, that means that after 5 trials we still did not have a head, but on the 6th flip we got our head. So that's how the data looks here, and we've got it in a scatter plot. You can see that that scatter plot is following a decreasing curvy trend. Now, I'm going to leave this alone for just a moment. We'll be back here for sure, but I'd like us to think about how we can transform this data set so that it resembles more linear. That's what we need. So there are lots of situations. The situation that we just looked at where we were counting the number of trials until you got ahead, that is an exponential situation. But some others that you're familiar with from high school, population growth is often exponential. Growth or decay. You might remember a little bit about depreciation or half-life. All of those are situations where things are growing either exponentially or decreasing in an exponential fashion. An exponential curve, folks, can be linearized by it's kind of shrinking the y-axis, and you can do that by taking the log of both sides. And I'm going to use natural logs here. I just want to remind you a little bit of the algebra of logarithms, which you learned in your previous algebra and trig classes. But if we write this or take the natural log in both sides, here comes the algebra. The natural log of y will equal, and then it's the natural log of whatever's over here, a b to the x. Now we're going to remind you some of the properties of logarithms. When you see a multiplication like this, you will remember that the log properties say that if we have a product here, we can break that out as an addition. So this would be the natural log of a plus the natural log of b to the x. But we can go farther than that. You'll remember that the power rule says you can bring that x down in front. And here's our final result. The natural log of y will equal the natural log of a plus x times the natural log of b. Ladies and gentlemen, the interesting thing is, as you look at this equation and you look closely, you will see that we have a linear model, really. Y equals over here. That's the constant part, or the y-intercept. Here's the slope, the natural log of b, and there's the x. So we really have an equation that's in the form of y equals mx plus b, if you will. So what I'd like us to do, we're going to see how you can do this in your calculator. So we don't have to actually take logs. We just had to get a little background in how to use them here. What we're going to do is put our data set in lists 1 and 2, and then we'll ask the calculator to take the natural log of the y values, because that's what we need here, the natural log of y. So I'm going to go grab my calculator, and you can see I have my data. In list 1 I have the number of turns it took to get heads. In list 2 I have the number of times that happened. So what we're going to do is ask for the natural log of the y values. So we're going to come over to our list 3 up on the title and just tell it the natural log of what's in list 2, our y's. Again, the reason that we're doing this is because if we look at the natural log of y, then we can operate in a linear mode, and linear is what we're familiar with. So we let the calculator do the work. What I would like to have you do is take a look at the scatter plot that now is our x's versus the log, or the natural log of y. I believe that we'll see that this is way more linear, and that's what we're going to put on that graph square on the other page. So let's back up there and let's call up a scatter plot. Here are my plot 1 settings. I don't want to look at plot 2 though, so I need to change things a little bit. I want my plot to be 1 versus 3. My x values versus the natural log of y. And we're going to plot that. Setting up a window. Okay, I'm ready to view my scatter plot, and I must admit I cheated a little bit. I asked the calculator for a zoom 9 window, but then I adjusted it so that we can sketch here. Our toss numbers go from 1 by 1, so toss 1, 2, 3, 4, 5, and 6 is as high as we go. The natural logs of y, the natural logarithms of the y values, go between 0 and 6. And again, I kind of cheated because I looked at the window it set and then I adjusted it so that I could make my plot on paper. And okay, here we go. Let's take a look at that scatter plot. Well, we can find those values by using the trace key judiciously. When x is 1, the y is about 4.5. When x is 2, the y is about 4.1. When x is 3, etc. And I'll go ahead and plot these. That definitely looks a lot more linear than what we started with, and that's the beauty, folks, of using that transformation model. That is, we took the natural logs of y and plotted them against x. We linearized our data set. We didn't change our data set, we just changed its scale, if you will. Alright, so we've looked at the plot. We need to find that regression equation, stat and calc, and I'm going to choose this time not number 4 but the other model, the other linear model, because that looks like more like what we have written up here, constant plus b times x, and that is a linear regression. So here's our stuff. The natural log of y is equal to, let's see, arrow through there because I'm good. According to them, A is 5.273, about 5.273 minus, or I'm going to put plus a minus, 0.671 approximately, just carrying things out to the thousands place, times x. Y'all look at that value of r there. That's very strong. Okay, we've got ourselves a pretty good linear association, and we got it by taking the natural logarithm of the y's and plotting it against the x's. Alright, so here's our model. Alright, we want to be able to get this back to a form that we recognize. So we're going to do a little bit of work here, okay, just a little bit, and we're going to convert back to exponential form. Let's put both sides of our equation into exponential form. That's what it says we should do. So I'm going to choose e as my base since I have natural logs here. E raised to the natural log of y is equal to e raised to the, and it's all this stuff, 5.273 plus negative 0.671x. All right, we can do some simplifying. You remember up here we took things that were scrunched together and pulled them apart. Now we've got things that are apart, we're going to put them together. So our next step in the work here, well, e raised to the natural log of y is just y. Some of you will remember this is saying e raised to the power that you raise e to get y, well, it's y, is equal to, and now this is an addition. So we know that that is going to come together as a multiplication. So we're going to be looking at e to the 5.273 times e to the negative 0.671x. Well, some of you will be thinking, okay, power to a power, that x doesn't have to stay in there. In fact, you'd be absolutely justified in doing this. Y equals e to the 5.273 times e raised to the negative 0.671 all raised to the x. And now we're back totally in exponential form. Number times base raised to the xth power. Now the deal is e to the these things, those are numbers. We can find those out. So I'm going to write this equation with those in number form. So I need to have e raised to the 5.273 power, and that is around 195, real close. E raised to the negative 6.71, and that evaluates to about 0.511 all to the x. Starting times base raised to the xth power. There's an equation for what we were looking at. Now you'll note here that we went to a lot of work. First we took the logs and showed the algebra behind that. Then we came down and transformed it back into exponentials because that's what our data is. We want to be able to talk about a growth or a decay rate in an exponential. And here's the deal. If the value of b, this, okay, is bigger than 1, then the growth rate is b minus 1. That's not the case for us, however. We have a decay situation because the number here is between 0 and 1. The decay rate will be the opposite of that, 1 minus b. So our decay rate in this problem would equal 1 minus 0.511, which is 0.489. Oh, it should be close to 1/2, since every time your chances of getting ahead are around 1/2. So our decay rate is that much. That is about half of what we have left turns into heads the next time we do it, which makes sense. Now, ladies and gentlemen, I don't want you to be frightened by this. I just wanted us to walk through this one time so that we could see what's really happening, y'all. You'll remember that we have all kinds of regression models built into our calculators. If we recognize from the first that this was an exponential model, then why not ask our calculator, you might say, why not ask it for an exponential model that fits? See it right there, expreg? I'm going to go ahead and hit enter, and we're looking for data now. Back to our live data, list 1 and 2. Okay, we know the transform thing works, but let's go back here and say, all right, this is what they say when we did the exponential reg. So if we recognize that this was an exponential, look at the equation that they got, their values for a and b. This is what their expreg said. It said that y was equal to a starting point of 194.9 times a base of 0.511, approximately raised to the x power. And ladies and gentlemen, that's very, very, very close to what we said. And remember how when we did our linear regression, we came up with this value of r? The calculator, when you tell it to do an EXP reg, it is giving you the value of r that you would get from doing the linearization. So the point of this was to drive you crazy? No, it was not. It was to show you how the calculator comes up with the equation for that EXP reg and why you are justified, folks, in saying that an r value of about negative 0.989 is appropriate for this data. Remember, r is supposed to be about linear stuff, not about exponential. But they are using this because when you linearize the data using logarithms, right, the opposite of exponents, then you get an r value, or Pearson's correlation coefficient, of 0.989. Now, that was a long and drawn out explanation. Again, we're not expecting you to be masters at taking the log here, but we just wanted to show you what it looks like. Let's look next at this little example. This is taken right from your textbook, folks. We have some information about the length of an alligator versus its weight in pounds. Length in inches versus weight in pounds. And if you think about that relationship, if length is measured in inches and these things grow in 3 dimensions, since they're 3-dimensional objects, then a power model, that is y equals a times x raised to the, it's got to be close to 3rd power, one would think, should make sense. A power relation like this one, where x is not in the exponent now, okay, but x is being raised to a power, that one can be linearized also by taking the log of both sides. Alright, so I'm going to ask you to think about the algebra of that with me again. You could do this with natural logs or logarithms. Both work the same way. But if you think about taking the log of both sides, then the log of y would be equal to the log of, and we have ax to the b power. That's a product, and so we know that that breaks out with an addition, remembering back to our algebra days, that would be the log of a plus b times power rule as well, plus b times the log of x. Notice, folks, that this time the log is of x. Oh, when we did this before with exponentials, I'm just going to go back for just a minute. Here, the only thing that had a natural log with it were constants and the y, right? Over here, different picture, log of x. So if we're going to do this in our list, we'd having our data in list 1 and 2, where list 1 is the x value and list 2 is the y. Then in list 3, we would put the log of list 1. Okay, that would be the log of our x's. In list 4, we'd put the log of our y values. Right, so the log of list 2. And then call up the linear regression for L3 and L4. Again, if you look at this, folks, we are in a linear model here. We've got a y equals a constant plus a multiplier times the log of x. That's a linear expression. So you call up the linear regression for list 3 and 4. The regression equation is what we had above, that the log of y is equal to the log of a plus b times the log of x. And if you look in your textbook, you can see the specific numbers for this alligator problem. But to put it back into power form, that's just going the other direction. You would say that the log of y, so we're going to just do the reverse algebra now, would equal the log of, and we got to scrunch things back together. Here it was a plus, so that means that they come back together as a multiply. The b pops up to the top because of the power rule, log of ax to the b power. And then you'll remember that if we've got logs on both sides, then we can just operate with the constants, and that puts us right back here, y equals ax to the b. Again, just a brief little foray into how those logarithms work. If you had a situation like this, then I want to just direct you to your calculator. You could go through the log transformation if you want. Some number crunchers are going to want to test that, but I got to tell you that there is a power reg feature. See it right there, A? Something that you know is a power model. A power reg will do the same thing for you. It will give you a value of R based on this whole logarithmic thing, but that value of R will be a good indicator about how strong the correlation is in that power model. All right, last thing we got to talk about. This is a power transformation. The radius of some circles versus their area. And folks, we know what this relationship is. We don't have to guess around by doing logarithms. We know that the area of a circle is equal to pi r squared. So if we wanted to linearize these y's, what we could do is take their square root. That's the inverse operation. It says let's try it and see if our new plot is more linear. Folks, I'm going to challenge you to do that. I'm going to go ahead and put this data into my list. Okay, I have my data into my list, and the idea is, since we already know the relationship between the radius of a circle and its area, that we should be able to linearize just by taking the square root of these things. So let's make our list 3 equal to the square root, so second and the x squared key, and we want the square root of list 2. And we should check a plot. So let's get our scatter plot set up to look. And it is looking at 1 and 3. I'm going to cheat and use the zoom 9 window. Oh, yep, I'd say that's a little bit more linear. That's definitely, most definitely, way more linear than this. And again, the idea is, for sure, is it more linear? Yes, it is. The idea is, if we already know the relationship, then we don't have to mess around doing the log-log transformation. We can just do the inverse of the thing, of the power model, and be pretty much assured of linearizing the data. Okay, ladies and gentlemen, that's been a very intense algebra lesson. Okay, I would like to ask you to get out there and do that try as quickly as you can. And in class tomorrow, we will have an opportunity to work on several problems that require us to do some regression that's not exactly linear. All right, have a good night.